We're examining related rate problems here in this video. The purpose of these next few examples will be to show you how to sometimes simplify the equation we're using before we attempt to use derivatives, where we might be able to avoid using things like the product rule if I can simplify my expression first. So here's an example. I've got a graph of a function. I'm going to tell you the equation of that function is y equals x squared. Now imagine me putting a point on the graph in the first quadrant and then drawing a rectangle by just drawing a horizontal line until I get to the y-axis and a vertical line until I get to the x-axis, and then just connecting the other two sides to the origin. And so that leaves me with this shaded rectangle here. Now, if I wanted to find the area of that rectangle, that would be something not too hard to do. I could just take that coordinate, and the x coordinate would become the width, and the y coordinate would become the height, and we know that the area of a rectangle is base times height. However, let's take a look at this in motion here. Imagine that that point can actually move through the first quadrant for a few seconds, and so notice that the rectangle's area now is changing as we go. And what we're interested in this related rate problem is, as I control that timer and we go for about 3 seconds, watch as we just go past the 3-second mark. And as I slow it down here now, we want to know as we go through as we get just past the 3-second mark here, and the x coordinate is 3 and then a little bit past it, you know, as this thing moves, how many square units per second is the area growing by? Okay, I can measure the area at any given moment, right? That's understood. I can measure the area at any given moment, but how fast is it changing? And that makes it a related rate type of problem. So let's examine this one. Let's examine this now. The first step in all related rate problems is to start by mentioning what we know and what's changing and the equation relating all the variables. Okay, well, I'm actually going to start with how I measure the area of this rectangle. Okay, well, in general terms, area of a rectangle is length times width, or base times height. Okay, but in this situation, that's all determined by this point on the graph right here. Let's actually just label, you know, that point has an x coordinate and a y coordinate. And the value of x, as it changes, remember this is just a still shot of the moving point, so this is not meant to be any specific value in mind. This is just a sample of where that point goes. Remember, it moves along the curve, but the x coordinate of that point at any given moment would determine how wide the rectangle is. And like right now, this point P, the x coordinate appears to be about 1.9, 1.8. So that would be determining the width. And the height of this point appears to be just a little bit over 3, like maybe 3.2. So that y coordinate would be the width, the height. So to write it in the context of this problem, if I know the x coordinate of the point and I know the y coordinate of the point, multiplying those together would give me the area. And normally at this stage, we would say this is the equation that we want to study. And so since we're really wanting to find the rate of change of the area, I'm going to start making a list here. We want to find the rate or derivative, and that can be expressed a prime, or sometimes in related rate problems we write it this way, just to show, hey, we're finding the derivative or the rate of a with respect to the time t. Remember, it's implied that the area is a function of the time, right? As the point moves for those first few seconds, the area is affected by that. So area is a function of time. We're also given how quickly the x coordinate of this point changes. given that dx dt, in other words, if I were to examine this point from the perspective of the x-axis, the x-coordinate is moving to the right. The x-coordinate is changing by going to the right 2 units per second, which we could also abbreviate, that's x prime of t, or x prime. And the x-coordinate that we're interested in is 3. Okay, so in other words, as this point climbs up here and climbs, as the x-coordinate or the x value, in other words, as the width of the rectangle passes through 3 units and goes beyond it, at what rate is the area changing right then? Okay, so this x is not a constant. It's just the instant that we're solving the related rate problem. Now, it might be worth noting that if we were at x equals 3, then of course, because we're on the equation y equals x squared, y would be 9. Okay, y would be 3 squared. So that could be, that wasn't given, but that's implied by the problem, because if this is the graph y equals x squared and x were now 3, this would be the 0.39. Now, I actually find the problem easier to solve if I actually use that other equation, that secondary information, very important information, that y equals x squared. Okay, so that automatically allows me to find the complete ordered pair as long as I know one number, the x. And what that allows me to do is actually express the area all in terms of x. Because I can substitute, because no matter where I am on the curve, y is always x squared. And what that allows me to do is, using algebra, just simplify the right side. That the area of that rectangle now is completely determined by the width. If I know the width is x, then the area of that rectangle is going to be that number cubed, simply because in the construction of this problem, y is always x squared because of the function that this point lies on, right? So if I define that curve to be another function, then whatever that function is, that would be the substitute for y here. And I now have an equation that's only in terms of x, which is going to make my derivative that much easier. So we're going to apply the derivative with respect to time now to both sides. Remember, we use the chain rule both times. So the derivative of a with respect to t, we could write dA dt, but a lot of you just want to use the prime notation. And on this side, this is now the function. This is now a function of a function, because function x of t is being raised to the power 3. So the derivative of x cubed is 3x squared times the derivative of x. And these derivatives stand for the rate at which each quantity is changing by. So now we can use the given information that the x-coordinate is changing by 2 units per second, and we're solving this at the instant that the x-coordinate is 3, and we're finding a prime. So it looks like this time all I've got to do is evaluate the right-hand side and take 3 times the 3 for x squared times the derivative of x, or the rate of change of x, which is 2. And so we'll multiply this together. This ends up being 3 times 9 times 2, which I end up getting 54. So now the label of this one would be, remember, this stands for dA dt, which that notation sometimes helps construct the label, because it would be the label of area, which would be square units, divided by the unit of time, which in this problem is seconds. So my answer in this instantaneous rate is the rectangle at the instant that the point is the 0.39, and growing past it, it's going to be growing at a rate of 54 square units per second. Follow-up to a question like this, or in a very similar one, is to study the rate at which the perimeter of this rectangle is changing. Now, that's not a problem laid out in our notes, but in your assignment, you do have one about the perimeter. So as long as you know how to find the perimeter of a rectangle, which we know is 2 lengths of each side, we might call it 2x plus 2y. You could make similar substitutions so that the entire perimeter is expressed in terms of x, also making the derivative be only in terms of x. So here we have a problem about a gravel pile. Now, you may not have been to a rock quarry before, but you certainly have probably witnessed a situation like this on a much smaller scale, like at a beach, and you dump sand out of a bucket and it forms a pile the shape of a cone. And every pile of gravel has its own proportions. By that I mean, every cone has a height and a radius on the bottom circle, and every cone has different proportions. Like sometimes you could have a cone where the height and the radius are the exact same. You could have one where it's a lot wider than it is tall, or in some cases it might be really tall and not as wide along the bottom. Okay, so in this particular situation, I have this gravel pile we're working with. There's some information about those proportions buried within this paragraph here. Okay, so let's read the whole situation first. At a sand and gravel plant, gravel is falling off of a conveyor, okay, similar to what's in the picture here, onto a conical shaped pile or a cone shaped pile at a rate of 55 cubic feet per minute. The diameter of the base is approximately 3 times the height. When the pile is exactly 8.2 feet high, determine the following. And so our first question is, at what rate is the height of the pile changing? So this is an indication of find the height's derivative, or we sometimes write that as dh dt, the derivative of the rate of change of h with respect to time. Now, some useful information in this problem is that the shape is a cone and that the volume of this cone is expressed this way. The volume of any cone is always pi over 3 times the radius squared times the height. Now, I'd like to also introduce this other information that was given in the paragraph. It says the diameter of this base. Now, the diameter is the whole way across. So the diameter I'm going to call 2 times the radius. Okay, but that's really the diameter, is about the same as 3 times the height. So instead of calling it d equals 3h, I'm going to use 2r equals 3h simply because the radius is a variable in this equation up here. So what this actually allows me to do is get this entire equation about the volume only in terms of the height, because in my problem A, I'm asked about the rate of change of the height. I'm asked nothing about the radius at all. So if I take a minute and just solve 2r equals 3h, and for r, it ends up being 3 times h divided by 2. But what I really want to substitute for is this quantity r squared. And so at the same time, I'm just going to square both sides. So if I square r, it's r squared. And if I square this side, it's going to be this whole fraction times itself. That would mean 3h times 3h, or 9h squared, over 2 times 2, which is 4. And what that's going to allow me to do as I start my problem solution here is to substitute for r squared. R squared was 9h squared over 4. But everything else stays the same. So pi over 3 was a constant. H is the height. That's not squared. I did that by accident. But the radius squared is the expression 9h squared over 4. Now, this still looks like it's a big multiplication problem, but the derivative is not going to require the product rule if I clean this up one more time by me noticing that a lot of this is constant. I'm circling all the parts that are constant right now. The fraction pi over 3 times the quotient 9 over 4. And so if I think about multiplying all that into one fraction, it would give me the quantity 9 pi over 12. that is all a constant, and so the only part that's really changing is the h. And if I take h squared times h, that's going to be h cubed. So the importance of this is that my volume is entirely expressed in terms of h, and in my related rate problem, I'm given the rate of change of the volume because the conveyor shoots off 55 cubic feet of gravel per minute. And we're studying this at the instant that the pile is 8.2 feet high. So all I'm going to need is information about the volume and the height. And that's why this is this important way of writing the equation now, because it only involves the height and the volume. So now it's time to apply our differentiation rule. We're going to apply the derivative with respect to t to both sides. And that means that v prime, or dv dt, on this side, all I've got is this big constant times h cubed. So we use the constant multiple rule and the chain rule. So the constant is 9 pi over 12, and then the derivative of h cubed with the chain rule is 3h squared times h prime. So all that's left to do is fill in the given information and note what we're solving for. We're finding the value of h prime, given that the derivative of v, or the rate of change for the volume, is 55, and that the height is 8.2. So let's fill it in here, starting with the derivative of v is 55 cubic feet per minute. The constant 9 pi over 12 starts the right side, 3, and then the height is 8.2. We're squaring that quantity, and then h prime is the variable that we're left to solve for. To avoid complications entering this into my calculator in a minute, I'm going to type all of this into my calculator first, and then I'll know what I'm going to divide by both sides. I encourage you to pause the video right now and also grab your calculator and work out a number for this entire quantity here. So I went ahead and added this, or multiplied this right-hand side quantity in my calculator, and I got the final value there, 475.291, and there's more digits here, 55, etc., times h prime. So my last step then is just going to divide 55 by the answer I just got. I'm going to grab my calculator and do that. And so my value is 0.1. I got 1157, which for 3 digits we'll call this 0.116. Now, remember, this could also be called dH dt, and so that actually sometimes helps with the labeling of the answer, simply because I know the height of the pile, h, is measured in feet, and the time in this problem is measured in minutes. So the label of this number should be 0.166 feet per minute. The height is growing very slowly, less than a foot per minute.